Okay, sure. I mean, it's a great pleasure for me to introduce Yongxin Chen, a professor of aerospace engineering from Georgia Tech. He has done some interesting work on safety assurance of stochastic systems. He's a winner of numerous prestigious awards of IEEE Control System Society, including George Axelby Outstanding Paper Award, and many other awards that recognize accomplishments of junior researchers like Ekman Award, A Square, C Square, and many others. So Yongxin, with that, I let you take the stage, and I mean, as people join, they should be able later maybe to watch the recording to catch up with the beginning if they miss some. Okay, thank you. Thank you for sharing your time with us today.
Yeah, thanks for the invitation. So today I really want to share some latest work on safety control or safety verification specifically for stochastic systems. This is based on a joint work with my collaborator, Saber, and also my student, Zishun and Li Chen. And so this talk is mainly based on these two papers. One is about reachability analysis, and another one is more general, is about safety verification, both on stochastic systems, stochastic nonlinear systems. Okay, and I think safety is important. Everyone knows it plays an essential role in almost all the real-world applications, especially applications involving human kind of in the loop. It's very critical. Actually, this is one of the major obstacles to deploy many autonomous systems in human life these days. So I think this is all clear. So I would jump to the technical part immediately. So once we understand that safety is important. So how do we ensure safety of autonomous systems? So in control community, we have developed a few methods. So two very popular ones include the barrier function and the reachability analysis. So the barrier function works in this way. Basically, it's normally when you do this safety insurance, what you have is you have a set which you know is safe. Right? Like for instance, when you drive, you have to drive on the right lane. Right? This means what safe means, and barrier function basically ensures safety by make sure this set, the safe set, is forward invariant for your control dynamics. In that case, you can just easily see because the system is going to stay in this safe set forever. So of course you are safe. So that is basically how barrier function works. And the reachability analysis is slightly different. So what reachability analysis does is basically predict all the possible future, right? All the possible futures. Like when you do this, when you take a left turn, depends on the accuracy of your turning, then you have many possible futures, right? Then if each of these possible future is safe, then you are safe. So reachability analysis is basically a one way to approximate all the possible futures in certain structured way. Then you just want to, if you want to use this for safety verification, you just want to make sure this reachable set is safe. So that is how it works. Okay, both methods are very popular, especially for deterministic systems. And our work is more related to the second one, so reachability analysis. And yeah, we have this very nice method, but still, there are still many challenges that remain to be solved for safety, safe autonomous systems. So here I list a few that is most relevant to our work. So this, for instance, normally the dynamic system you have may have high dimension. Like for instance, if you have a vehicle, you have this space, I don't know, it's like 6, right? If you have a quadrilateral, it can be 12 or even higher. So this is a very large state space. And this type of high dimension would induce very large computational cost if you want to use certain type of method. So this basically means computational complexity. Then another one is nonlinearity. When things are linear, there are many structures you can explore. Less things becomes significantly simpler in the linear setting. But for general nonlinear systems, you have much less structures. And how do you handle safe control for nonlinear system? That is a very difficult problem. And another one, which is actually most relevant to this talk, is uncertainty. So if your model is perfect and if there's no uncertainty, it's deterministic completely, then the best way to ensure safety is to just simulate this trajectory, because you only have one trajectory. That's very cheap to do. Then if this one is safe, then you are safe. But unfortunately, this is not the case due to uncertainty. We have many different type of uncertainty here. So that's the focus of the talk, safety verification under uncertainties. Okay, so what type of uncertainty we have? In the community of control, normally we consider two types of uncertainty. One of them is deterministic uncertainty. And this type of uncertainty, normally they are assumed to be bounded. And other than that, you don't know anything about the uncertainty because you don't know the statistics. They could be correlated, uncorrelated, you don't know. And normally for this type of uncertainty, what you want to analyze is the worst case behavior. So you want to make sure the worst case behavior is good enough. So this is the uncertainty model used in robust control. Okay, this is the main uncertainty used in this safe control community these days, I can argue. But there is another type of uncertainty also plays an important role in application. That is stochastic uncertainty. So very different from deterministic uncertainty. Stochastic uncertainty worries about performance in average. And stochastic uncertainty normally is unbounded. For instance, the disturbance can be a Gaussian random variable. And the good thing about the stochastic uncertainty is normally you know the statistics. You can learn these statistics or something people already know is a Gaussian, sub-Gaussian, these type of things. Okay, so this is a very different type of uncertainty model. And this is the main uncertainty model used in another branch of control known as a stochastic control. So both uncertainty would appear in practice very often, and they may appear simultaneously. Okay, so the goal of our work is to really, this is our goal. We would like to have an effective and scalable approach to safety insurance for general nonlinear systems, and both deterministic and stochastic uncertainty. So these are the two typical models we would consider. So the first one is continuous time. The second one is discrete time. So the continuous time, this D is the deterministic uncertainty, and the dW is the Brownian motion. This is the stochastic uncertainty. So we would focus on this model in this talk, and other techniques we develop can be equally applied to the discrete time system. You can find these details in the paper. So here I want to emphasize that what we would like to do is, of course, we consider both uncertainties. And the very important thing is we would like our approach to be scalable to high dimensional system. And we would like our approach to be effective so it doesn't generate complete garbage. And we would like our approach to work for general nonlinear system, not just linear system. Okay, so these are the things we want to keep in mind. So this is the outline of the rest of the talk. I'm not sure if we have time to cover everything in detail, but I will start from the first one, which focus on reachability analysis. Okay, so reachability analysis. What is the reachability analysis? So let's take a look at the definition of reachable set first. So for deterministic system, okay, So definition of reachable set is very simple. So this is your deterministic system. Okay, so you have your state, you have some disturbance. Okay, so then the reachable set at the time instance t. So normally you need to fix a time instance, can be any value. Basically is all the possible values of the state at that time instance. If that state comes from this system starting from certain initial condition and certain disturbance. So it's something, in principle, if you can simulate this system millions of times with all the possible initial state and all the possible disturbance, you can get this. And this is not the most effective approach, but this is one way, and this is the definition. Reachable state, where the system can reach, okay, reachable set. So this is a great definition, but this definition is a bit too conservative for stochastic system. I think to see this, let's just look at a very simple example, which basically means your dynamics is just a Brownian motion, which basically means you are doing random walk, complete random walk. What happens here is because this dw is a Gaussian noise, so roughly at any xt, this is a Gaussian random variable, and we know Gaussian random variable can take any possible values in the entire space. So which basically means you can reach the entire space. In this case, this definition would give you the entire space to be the reachable set, but that is not going to be very useful for application. Okay, so basically you are saying that I can reach any possible state. Okay, so that's why in stochastic systems, you need a better definition of reachable set. And this is a very popular notion of reachable set for stochastic system, which is called the delta probabilistic reachable set. So the definition is more or less the same. You have some initial set, and you have this is the deterministic disturbance set. And then the difference is you have some delta, which you can view this as a confidence level. Then the delta probabilistic reachable set at the time instant t, which denote to be this, is basically the set so that the state can reach in the set with probability 1 minus delta, greater than 1 minus delta. So it's approximation of other possible reachable set, but with high probability. So there are some corner cases that can get outside this reachable set, but that's fine as long as the probability for that to happen is very low, then it's not the issue. So this is a much better definition for stochastic system. It's much less conservative. So how do we, so here, our goal is to find a really scalable way to estimate, to approximate this delta probabilistic reachable set. How do we do that? So our approach is called the separation strategy. So the idea is very simple. So because our system is stochastic, what we do is we first couple this with a deterministic system, which starts from the same initial condition and driven by the same deterministic disturbance. So this part is the same as this one. So if you think about this, you can imagine that the trajectory, the stochastic one, is going to oscillate around the deterministic one due to the randomness. Okay, so you would oscillate, so or fluctuate. So if you can quantify this fluctuation, then you roughly know the reachable set of. You roughly know what are the possible values of xt, and this is basically the idea. So we denote this type of trajectory between this stochastic system and this deterministic system to be coupled because they are associated trajectory because they are very close to each other. So based on this intuition, we develop this separation strategy. So basically, what we do is now you have a deterministic system, and let's say you use certain algorithms to compute the reachable set for the deterministic system, where you do have many methods available already. And if you know the fluctuation, okay, of this stochastic trajectory around this deterministic trajectory is not much. So the probability for this to be less than a certain value is very high. Then it's very easy to argue that the summation of this set with this ball, so this is the ball with this radius, is going to be a delta probabilistic reachable set. So this is our approach. And this is the illustration. So basically what you do is you compute the reachable set for the deterministic system, and then you compute this radius for this ball. Then you take this type of summation, between two sets, which can be done very easily. Then you get a larger set. Then you can argue this larger set is going to be a delta probabilistic reachable set of the stochastic system. Okay, so this is the strategy. So thanks to this strategy, the problem we care about essentially reduced to estimate this. How can I get a good estimation of this ball so that this estimation is not very loose? So the problem, our reachability analysis problem now reduced to this problem here. So basically it's how to develop a tight bond, this R, the smaller the better, of this stochastic deviation, which is the fluctuation, the distance here. So this is what we achieved. So how do we quantify the distance between these two trajectories, right? If both trajectories are deterministic, there's a famous theory known as the contraction theory that can do this job. So what is the contraction theory? Contraction theory is based on something called a matrix measure, but let's not worry about this. So basically, you can think this as one type of property of your system. So let's say you have a deterministic system. If you know the system is contractive, it's just a notion. It's a certain property, and C is the contraction rate. If C is negative, we say this system is contractive, but the C can be positive, so then you can always do this. Okay, and this property is equivalent to this property. And thanks to this contraction property, now you can actually bound the distance between arbitrary two trajectories. And the distance can be quantified in this way. So if C is negative, which means the system is indeed contractive, then you will see they would converge to each other, so which can be seen here. So, but even if C is positive, you can still quantify the distance between them. So in this paper, we consider all the possible C. Okay, so and the way to see this is also very simple. Basically, you define a Lyapunov function to be the distance, then you take a derivative, and you get this inequality here. Then immediately you can conclude this. So this is the key of contraction theory. It works nicely to bound the distance between arbitrary two trajectories of a deterministic system. So this is great, but what we have is a stochastic system. Okay, what do we do? So it turns out the same thing can be easily applied to stochastic system. So here now we have a stochastic system, and we make the same assumptions as the contraction, and we assume another assumption, which basically means the coefficients for the disturbance is bounded. So that is a standard assumption. Okay, then it turns out people have done this a long time ago. You can still use the distance between the stochastic trajectory and deterministic trajectory as your energy function. Then you can calculate the energy function evolution, and you need a little bit of Ito calculus here, but it's a standard calculation, so you can conclude. Basically, for stochastic system, you can also conclude the MSE, okay, between these two trajectories can be bounded above, okay? And this is in terms of expectation. Now, if you want to know the probabilistic bound, which means this distance less than a certain thing with high probability, you can apply Markov inequality, or the same as the Chebyshev inequality. You get this result. So this, you conclude the probability for the distance to be less than this value here is greater than or equal to 1 minus theta. Okay, so this is what we get at this point by just applying contraction theory directly. This is a reasonable result, at least I give you something. So the question is this a good result? Okay, so this is the result which was given in the literature when we started work on this. Is this a good result? So to see whether this is a good result, we try to specialize this result to linear system and see whether this is the best you can do for linear system. So this is very standard thinking. So here, let's specialize our system dynamics to a linear system, which looks like this. It's a very special linear system. So now what we want to see is we have a stochastic system and we have a deterministic system, and this C is a scalar even, and also the contraction rate. Now we want to estimate the distance between xt and xt. And based on the result we get on the previous page, this is what you can conclude. Okay, you conclude this is greater than 1 minus theta, this probability. But for linear system is very special. Even for stochastic system here, you can see actually xt is actually a Gaussian random variable. And actually you can even compute the covariance, which is given by this. So the random state xt is a Gaussian random variable whose mean is locus xt and the variance is this one. And we know for Gaussian random variable, you know the expression is e to the power minus x squared, something like this, right? So the probability decays to 0 extremely fast. And thanks to this, what they call light tail behavior, what you get is you can actually compute. You can say that the probability for the distance to be less than this value here is greater than, the probability is greater than 1 minus theta. Okay, so this is what you get for the linear system. This is what we got on the previous page for general nonlinear system, which you can also apply this to linear system. You see, this result is much better than this result, because what we want is we want this radius to be as small as possible, because that is your confidence radius. Okay, so for instance, you see this radius scales like 1 square root of 1 over theta. So if you just look at this part, it scales the square root of 1 over theta. Where this term over here scales square root log 1 over theta. Okay, so let's say for aerospace application, normally you would like theta to be 10 to the power minus 10. Just say that's your, you need the system to be safe with this high probability. Then you can get the linear system, the result is about 4.8. So this radius is about 4.8. Where the nonlinear result we got on the previous page is about 10 to the power 5. So there's a huge gap between them. Right? This result is useful, where this result is completely useless because the radius is way too large. So you don't say anything meaningful. So this is the situation. We have a result for general nonlinear system, but we realize there's a huge gap between this and the linear result. So the question we ask is this gap fundamental? Or this is just because the way we did the analysis, our analysis is not good enough. So it turns out it is the second case. So what we did is we managed to remove this gap completely. So we established a nonlinear result, which is exactly the same as the linear result. Okay, so how did we do that? So clearly you cannot apply this analysis, what we did for linear system, to nonlinear setting, because nonlinear system, this is based on Gaussian, and nonlinear system, nothing is Gaussian. We cannot do that, but we can move to the next best thing, which is a sub-Gaussian distribution. So what is sub-Gaussian distribution? It's a generalization. It is the most natural generalization of Gaussian distribution. It's a random variable, a random vector is said to be sub-Gaussian, with this being the covariance, some type of a parameter. Okay, if this function here, which is known as the moment generating function, is bounded above by this number. And this theta is my parameter, and this has to be true for any lambda. And this L is can be any vector on the unit sphere. So this means the unit sphere. So the sub-Gaussian random variable basically asks you that the moment generating function has to be bounded above by a certain function here. And the Gaussian distribution is just a special case of this, where this is the variance, okay? And what's interesting about sub-Gaussian is that sub-Gaussian distribution shares exactly the same concentration as the Gaussian distribution. So if you have a sub-Gaussian random variable, then the probability decays to 0 very fast. So you can actually conclude the norm of x to be less than this value here. It has a probability at least 1 minus theta. And this is the same as the Gaussian case, okay, exactly the same. So therefore, one thing we can try is actually one thing we tried is that if we can show that xt minus xt, the quantity we want to bound, okay, is a sub-Gaussian random variable, then we can use this and we can get the similar result as the linear setting. But the problem is this is not true. So, okay, so this is not true. So this turns out to be not a sub-Gaussian. So what do we do? So the secret weapon we develop is known as the averaged moment generating function, which is a generalization, is the average of the moment generating function. So which is defined to be this. So this is the key. This is the average moment generating function. So if you remove, so this expectation is over the random variable, and this expectation is over the unit sphere. If you remove this expectation, then this is exactly the moment generating function, and this thing is the inner product. Okay, so basically is this quantity we defined here is the average of the moment generating function over all the possible L on the unit sphere. So this is the uniform distribution. So what's interesting is that if a random variable satisfies this condition, which I would explain, this is the relaxation of the sub-Gaussian distribution, then the norm of x shares exactly the same concentration, which means this inequality is the same as the previous one. But what's good is that this condition is much weaker than sub-Gaussian assumption. So the sub-Gaussian requires this moment generating function to be less than this quantity for any L. So here, the average moment generating function, this inequality only asks you that in average over all the L, this is bounded by this. So this is much weaker than asking for this to be less than this value for any L. Okay, so the details is not important. You can just think that we found a relaxation of the sub-Gaussian, which is much weaker than sub-Gaussian, but which shares the same property. Okay, then because of this, it turns out we can actually show the state we have indeed satisfy this condition, and the details will be skipped. But based on this tool, we develop this result over here. So we get for our general nonlinear system, we can conclude the probability of xt minus xt. So this is stochastic trajectory, deterministic one. The distance is going to be less than this value with probability at least 1 minus theta. And this is exactly the same as the Gaussian concentration inequality. So it's as good as a Gaussian. So, and this is basically what, this is just to show you how good this result is. So this is the bound, and this is the Monte Carlo simulation. So it's almost, there's no gap at all between the simulation and the gap. And also this is just to show you, this is really the best result you can get. And yeah. Yeah, so this is this part. And with this in mind, we provide a general recipe for reachability analysis for nonlinear stochastic system. So this is what you do. You have a general nonlinear stochastic system, what you do is you take out the deterministic part and you use whatever method you prefer to approximate the reachable set for the deterministic system. Then you take the summation of this set with this ball, with this radius, which you can compute. Then you can conclude this is going to be a delta probabilistic reachable set of this nonlinear stochastic system. And depends on what method you would like to use for the deterministic estimation to estimate this RT bar. You can get a different type of result. You can get probably more tighter result with more computation, or you can use a more scalable method and faster real time even. So this is the general recipe we would like to provide. Okay, so this is the first part of the talk. I see we are running out of time. Let me quickly go through the second part. So safety verification. So in the previous part, what we did is we provide a scalable way to compute the reachable set of the stochastic system. Okay. But if you think about what we need for safety verification for stochastic system, well, basically is you would like all the simulation. Let's say this is your unsafe set. You would like, and due to uncertainty, your system can take many different trajectories. You would like to make sure all the possible trajectories do not get into this unsafe set, right? So this is, and at least with high probability. So you would like this trajectory level safety. So the trajectory doesn't intersect with this unsafe set. What we did on the previous page is we found a way to compute the reachable set for every time instance. So we know when t is equal to 1 second are the possible reachable set, t equal to 2 seconds, or t equal to 1.5 seconds. Okay, but this doesn't directly give you the probability for the trajectory to not intersect with this unsafe set. So there's a huge gap. Okay, so this gap is fundamental. So how do we get this trajectory level safety guarantee? So one popular approach, or actually probably the only approach I'm aware of, is based on this martingale inequality. So what is a martingale inequality? It's one type of a stochastic process which satisfies certain property. So basically it's like the expected value of the future. So this is the future value of the quantity, and this is the current value. So the expected value of the future is always less than equal to the current value. So one way to think about this is like the gambling. If it's a fair game, so your expected value of the future money is always less than the current one. Okay. Then for this type of stochastic process, then there's a famous martingale inequality which tells you the maximal value of this stochastic process over the entire trajectory level greater than this is going to be less than this value here. So this is a very important inequality, and this gives you the trajectory level type of guarantee. So this is actually the foundation for this what people call stochastic barrier method. So almost all the safety guarantee on the trajectory level of stochastic system is based on this inequality. We are going to do the same, but our strategy is very different because the previous method need to design a very complicated. Actually, normally it's computationally infeasible to design this barrier function. Where in our method we don't have to do this. So let's take a quick look at what we did. We use this set. We use this what we call the separation strategy. So basically, again, what we want is we want to reduce the stochastic problem into a deterministic problem. And as we discussed earlier, the stochastic trajectory is going to fluctuate around the deterministic trajectory. Okay. If we can quantify this distance in the trajectory level, so now we want to develop a ball in the space-time. So which means we would like the trajectory to stay inside with high probability. Okay, so this is like a tube. And previous reachability analysis is like a ball. We only care about one time instance. So now we want to quantify the trajectory stay in the tube with high probability. So if you can develop this tube, which quantify the distance between the two trajectory in the trajectory level, then what you can do is you can shrink the safe set of the, you can shrink the safe, let's say C is the safe set you care about. If I can shrink the safe set with this tube, then if you can ensure the deterministic system is safe with this shrink the safe set, then you can basically ensure the stochastic system is safe with high probability with the original safe set. So it's the same as the separation strategy, it's just a different way of saying this. So with this, we basically reduce the stochastic problem into a deterministic problem. But the only thing we need to achieve this is that we want to develop a probabilistic tube. So we would like to estimate this tube so that the trajectory stay inside this tube. Okay, so that is what we did. And the details, it turns out we can modify the martingale in certain way and quantify this. And what interesting is the secret weapon, the average moment generating function, is in fact a kind of a martingale. And so we don't need to develop we can just use this specific function as the martingale. And with this, we roughly get this type of result. Okay, so the probability for these two trajectories less than this value, and this is for any t in the horizon you care about, is greater than this. And this is the radius. Okay. And this is very similar to the reachability analysis result. The key difference is now we would like the probability to happen for all the t. So the event is defined to be the trajectory level. And this is just to show you the result is tight, almost the same as Monte Carlo. And there's a small technique we need to use to make the result even stronger. I would skip this. The details can be found in the paper. So this is the general recipe we would like to provide to the user. So if you have a stochastic system and you have a set which you define to be the safe set, and you have some probability level you care about, then what you do is now you can compute this ball where the radius can be computed in closed form. Then you just shrink the set. So this set is going to be slightly smaller than this one. If you just shrink this set, and now if you can ensure your deterministic system is safe with respect to this shrink the safety set, then you can ensure the original system, stochastic system, is safe with respect to the original safe set. So in this way, we essentially reduce stochastic safety verification problem into a deterministic one, and then you can use whatever method you like. And that's basically is the end of the result. And just to show you a couple of examples, one example specifically. So you have a stochastic system like a unicycle, and you have several obstacles, and you would like to, you have some control. So I just do verification here, right? Then I want to make sure the trajectory do not intersect with this with high probability. Then what you do is you first, so right now for the stochastic system, all this area are the safe set because these are the obstacle. So what you do is you first make the safe set smaller, which basically you make the obstacle larger. And the amount of increase in the radius depends on the system dynamics, which can be computed in closed form. Then if you can ensure the deterministic system, now you see this doesn't have any randomness, doesn't intersect with this enlarged obstacle, right, in this way, then you can ensure the original stochastic system do not intersect with this obstacle with high probability. So you can do this for autonomous vehicle. You can do this even for more complicated tasks, which involves signal temporal logic, is more or less the same. And you can also do safe control on top of that. So this is one algorithm called a safe MPC, but you essentially reduce everything into deterministic problem and solve it. So this is a much more scalable approach. I think that's it. And these are some takeaway of this talk. So we basically develop a scalable framework for safety insurance for stochastic system. I think the key message I want to deliver here is our strategy is really reduce the stochastic problem into deterministic problem in a very non-conservative way. And then you can use the very scalable deterministic method to solve the problem. So this is going to be the key. And this is the list of papers we have written so far, and is growing. And okay, would like to thank my collaborator and my sponsor again. Thanks for listening. Any questions? I'm happy to take any questions.
Hi, Yongxin. Sorry, Petros, go ahead.
Okay, yeah, very, very interesting results. Thank you.
Thanks.
Yeah, just a general question I have. So the models you are using, the deterministic, for example, disturbance, what if you have uncertainty that is not exactly a disturbance, but it's more like the traditional robust control delta kind of block? I assume that analysis could carry over somehow, right? But or is it important to consider this? So that's my question.
That's a very interesting question. I think depends on what type of model uncertainty we have. So here, because we already consider deterministic uncertainty and stochastic uncertainty, for instance, in this example here, so this DT in principle can capture the one type of model uncertainty. Basically, is this delta model people use when the delta you only know is the known is bounded in a certain way. I think in that case, it's possible to convert everything into this framework. And another type of uncertainty, which is a parameterized uncertainty, which is not captured in this framework, is ongoing research, but that is indeed is not captured here. So basically two things. If it's parameterized uncertainty, it's not discussed in this talk. If it's just a standard bounded model uncertainty, I think you can put this inside this worst case uncertainty here, because people already use this for robust control. Yeah.
Right. Yeah. Thank you.
Hi, Yongxin. Nice talk. Can you talk about the sub-log growth in with respect to the safety probability? Because that seems to be a very important part. This square root of 1 log or square root of 1 over delta that you get.
Yes.
So will such guarantees be possible, for example, if instead of, say, using your method, somebody was doing, say, covariance steering, where you can only control the first two moments? How does your result compare to those ones when you have a delta which goes very small? So you want a very high probability of safety.
No, I mean, it's about, so I think these results are complementary. So what we want is a guarantee, right? So let's say if you do covariance steering for nonlinear system, okay, I think that's probably one thing you have in mind. You propagate the answer, the covariance, okay, and then you want to say something. When you say something, guarantee, what can you say? You assume it's Gaussian, then you can say something, but it's not Gaussian, you know it. And then you only have an estimation of the covariance. If you don't know any other information, the best you can do is this. The best you can do is this. If you only know the covariance, then the best you can do is this called the Chebyshev inequality, which is much worse. So if you know the it's not only you know the covariance, you know it's a sub-Gaussian, then you can do what we have. So I think the key is, I think the message is that if you only propagate the first order, second order moment, without any additional analysis, the best you can do is this one, which is square root 1 over log 1 over delta, if you really want guarantee. And what we did, you can imagine, is to ensure the random variable. So basically what we establish is xt minus xt is a relaxed sub-Gaussian. Okay, so this even relaxed sub-Gaussian means we not only control the first order, second order moment, we also quantify the high order moment. So you can imagine this is one way to, so basically we control also high order moment implicitly. So if you only have the first order, second order, this is the best you can do. Other than linear case. If it's linear, of course, you know. You see, if it's linear, you know first order, second order, but because you know it's Gaussian, you have many things to say. So it's implicit. Yeah.
So it's the arbitrary moment that leads to this log, the logarithmic growth.
Yes, exactly. That's a very good insight, because you see, what we bound is the moment generating function. And if you expand this actually capture all the moment. That's it. That's why they define this moment generating function. It's generate all the possible moment roughly.
Yeah. Okay. I see. So it's to put understanding on a claim that I've been reading, which is if you can control higher order moments, you get tighter tracking results, and this clarifies that it's because this log growth versus just 1 over delta growth for the first 2 moments. Okay. Thank you so much.
Yeah.
Hi, Yongxin. Nice presentation. I have a quick question. Like this is the perfect slide. I had this question. So, as you mentioned that the original moment generating function was not the suitable object to work with to go through these proofs. What properties of I understand that the sub-Gaussianness of this moment generating function over the sphere was somehow was important. What other properties of this, like what made this a suitable object? Like what is the intuition of working with this compared to the original? Like, do you have any insights on like how does this work with the proofs or something like that?
I wouldn't say you would know this beforehand. Right? We didn't know this beforehand. This is a very natural first attempt is to show this is sub-Gaussian. We try this, it doesn't work. I think we even have a counterexample so that this is not sub-Gaussian. And this is just one technique we learned from a different community. So it's clear this is the relaxation. Right? You agree with that because this is just average. So this is a relaxation. And just the proof works out. That's one thing. The proof works out. Another thing I would say a little bit more is that because here we only care about the norm. Okay. So when you only care about the norm, it makes sense to take the average. So actually, I skip the proof. Why? Even if you satisfy this assumption, you can still ensure this norm is bounded at exactly the same as the sub-Gaussian. So basically, I'm not sure if I can say this clearly, but the proof is extremely simple. It's roughly if this condition hold, okay? If this condition hold, roughly what you are saying is, I take a random unit vector, random unit matrix U. Okay, let's say X is my random variable. I take a random unit random variable random unit matrix. Okay, you know what the unit matrix is.
Yes.
U multiply X. Then what this inequality is saying is U multiplied by X is a sub-Gaussian.
Okay.
So this condition basically says even though X is not sub-Gaussian, but if you multiply a random unit matrix, which injects some other randomness, UX is sub-Gaussian, then because UX is sub-Gaussian, then you can bound the norm of UX, which is UX. But because U is a random, it's a unit matrix, so it's the same as X. So that's the key.
I see.
It's a very elegant thing. It's natural.
I get it. Thank you. Yeah, that was good intuition. Yes, thank you so much.
Thanks a lot for the interesting presentation. I also have a question regarding the class of dynamics that you are considering. You are always considering that there is a disturbance in the function f, but how about the function g? Can you also consider that there is a disturbance in this function?
There are more study needs to be done. So right now, you see this depends on how the way we model this. There are definitely some interesting study one can conduct. So right now we are using this assumption. So that is the first step. Definitely there are more structures you can explore. So to answer your question, okay, so what we care is really whether this coefficient is bounded uniformly. At this point, you can do some more local analysis, and this can be potentially done. So I think the answer to your question is if you know, even this depends on D and many other things, as long as this satisfies this assumption, which is globally bounded, there's no issue. So dependence doesn't matter. But if you want to zoom into this structure to get a better result, because this can be a loose bound, then that's something you need to worry more. We don't have that result yet. So, but
Okay.
Right now this assumption doesn't depend on the form of G.
Okay. And regarding the separation strategy, does it work in this case if you have a disturbance in the function G?
Yeah, I think it works because it works. Yeah, because this separation strategy only asks you that because it's only try to bound the distance between this one and this one for a given initial condition and also given the same dt. So you can still think as long as this is small enough, as long as this is bounded, whether this depends on dt or other thing, doesn't matter. This part is the same as this, so they are still going to be close to each other. So good observation.
Okay, thanks. And one final question, you mentioned in the beginning like two main strategies, control barrier functions and reachability analysis. I'm aware of some work about using control barrier functions for the same class of systems that you are considering here. Did you at some point manage to compare like the two methods, like what happens if you use control barrier functions for this problem? Did you compare or?
I would recommend you to take a look at the actually ACC paper.
Okay.
This is actually we use. So even though I emphasize that we focus on reachability analysis, what we did can be equally applied to barrier function and the reachability analysis. Because what we are really doing is we try to reduce the stochastic problem into a deterministic problem. So basically what we did in this paper is we kind of how would I say, we reduce the problem into a deterministic problem, then you can use the deterministic barrier. So if you look at this paper, remember we have some result to compare this with the stochastic. So I think one big limitation of this stochastic barrier function, okay, I could be wrong, but we did quite a bit of study. So most of the stochastic barrier function is based on this martingale inequality.
Yeah.
So I think the main problem, as far as I know, is how to design this martingale to make sure this is a barrier function for what you want. And this turns out to be a very challenging problem. First of all, it's computationally extremely heavy. So you don't have a good way to compute this. And also the way they define this barrier function, okay, it gives you very conservative result. So normally this barrier function can only give you this type of result, I believe. Because the barrier function normally you design can only give you this.
Okay.
Only in some certain very special case, like a linear system, where the one dimension, let's say, then the safe set is interval or something like this, you may be able to do better. But that is handcrafted. It's really, in general, this is what you can get. That's my understanding. And also it's not scalable. So, yeah.
Okay. Okay, yeah. Thank you very much.
Sure.
Yongxin, thank you for the wonderful talk. I assume we have no more questions, it seems, or...
Yeah, thanks for the invitation. Yeah, I think...
No, it has been a pleasure. And if you could share your slides, we'll post and advertise it on LinkedIn.
Okay, yeah, I'll share this.
Thank you very much for sharing your time with us today. Thanks.
Yeah, thanks. Yeah, hope to see you soon at some point.
See you. Bye.
Yeah. Bye-bye.